Yes, and methane that the past is a greenhouse gas that'll trap the sun's heat and change our climate too. Gee, is it hot in here, or is it just me?
Hi everyone, welcome to the video lesson for Monday, May 3rd and Tuesday, May 4th. Today in class we started learning about albedo and the greenhouse effect. We had a short warm-up, which we're not actually going to go over in this video lesson because it's kind of part of our notes. And then we moved on to our notes. So let's jump into our notes. So our notes start on page 2. So to begin, the Earth's atmosphere is divided into a series of different layers. Different things, different processes are occurring in each different layer of the atmosphere. There's different conditions, and they react slightly differently. But the layer we care the most about is the troposphere. The troposphere is where we experience weather. This is where all the clouds are, the winds, the high pressure systems, the low pressure systems, the jet streams. Everything that affects our weather takes place in the troposphere. This is also where the greenhouse gases reside. This is where they do their work of helping to keep the planet warm enough to sustain life. The ozone layer is not its own layer of the atmosphere. The ozone layer is a relatively thin band within the stratosphere. That's where ozone resides, O3. It's 3 oxygen molecules bonded together. And this is crucial for all of us because the ozone layer protects us from the UV radiation that comes from the sun. It absorbs a lot of UVC and some UVB radiation, which is what gives us sunburns. And if a bad enough sunburn, potentially skin cancer. So the ozone layer is very vital to our health. In Australia, where they have a hole in the ozone layer above their country, it's actually illegal to go out to the beach for a day without a hat because it is so dangerous. It is so likely to get sunburned and skin cancer that they want to make sure you have at least a little bit of protection from a hat. They can't really tell whether or not you use sunscreen. The Earth is constantly absorbing energy. The whole Earth system, the land, the oceans, the atmosphere, it's all absorbing about 240 watts of solar power per square meter. And this sunlight is what drives everything on our planet. This powers all those different things like photosynthesis, which powers each and every one of us. We get our energy from food. Our food gets its energy from photosynthesis. Now, it is a common misconception. A lot of people think that our seasons are affected by how close or far we are from the sun. Because remember, our orbit doesn't quite look like this. It's not really a circle, it's more of an oval. And some days we're closer to the sun and sometimes we're further from the sun. Our winter is actually when we are closest to the sun. Our winter and summer isn't determined by our distance, but because of our angle. Earth is on an axis. So when we have summer, we're actually at our furthest point from the sun, but we're tilted towards it, so we get more direct sunlight. Then during the winter, we're actually at our closest portion to the sun, but we're tilted away from the sun, so that's when we have our winter. So because of that tilt, and because the Earth is a sphere, the sun doesn't heat the Earth evenly. It's this uneven heating of the Earth that creates weather. When one packet of air gets heated more than a different packet of air, it rises. When that air rises, other air swoops into its place, and that's what makes wind happen. So the equator is warmed up more than the poles. I know that to us, our planet has a very wide range of temperatures. From the equator right now, if I were to go to Bahamas today, versus the poles and the Antarctic and the Arctic. But thinking about the whole of the universe, the range of temperatures that we see on our planet is actually very low. If I were to go down to the Bahamas on a super hot day, it's going to be about 30, maybe a little bit more than 30 degrees Celsius. But if I go up to the Antarctic or the Arctic, it's going to be a little bit below 0 degrees Celsius. That's not a huge range of temperatures in a universe, in a galaxy, that can go from negative 273 degrees Celsius to thousands and millions of degrees. So we exist in a very small slither of possible temperatures. And a lot of that is thanks to our atmosphere and our ocean. It's constantly helping to even out this temperature and to even out those heating imbalances that occur across our planet. Hot air goes up into the upper atmosphere. It tends to travel north towards the poles. It drops down, comes back to the equator, heats up again. It's helping to transport that heat around the world. Same thing in the ocean. The ocean water in the tropics gets very, very warm. It travels to the north and south poles, bringing some of that heat energy there. Then it brings that cold water back to the equator so it can get warmed up again. This is the Earth's heat engine, moving around energy, helping to distribute it around the globe so no place gets too hot, no place gets too cold. It helps to share that energy. Now, the Earth's heat engine isn't just redistributing the heat between the north and the south. It's also helping to move the energy away from the Earth. So it's not just different places on the Earth, but also away from the Earth. If we constantly took in heat energy, the temperature would continue to rise. Think about a pot of water on the stove. If I turn on the heat, it's going to keep raising its temperature until it starts to boil. Now, if you don't want boiling water, if you just want warm water, you're going to have an issue because you don't want it to get that hot to boiling. Now, on the stove, that's pretty easy. You just take the pot off of the stove. But the Earth, we can't really take the Earth out of the solar system. So what the Earth does is it doesn't just absorb all of the energy. It can reflect and re-radiate heat back into space. This is the Earth's energy budget. The Earth receives energy from the sun, but it also reflects it back into space. So not everything is absorbed. I'm able to reflect quite a bit of it as well. So I don't constantly heat up. I'm able to get rid of some of this heat and send it back into space. So this is my budget, looking at what comes in versus what goes out. So when the energy that's coming into the planet and the energy that's leaving the planet is equal or about equal, then it's balanced. Then we call that a radiative equilibrium. What comes in is equal to what goes out. When the amount of energy in and out is relatively equal, then my temperature is going to stay relatively stable. Any heat energy that's lost to the universe is regained. Now, anything that can disrupt that balance, anything that can increase or decrease the amount of energy that makes it to the planet can drastically change the temperature. On the right hand of this slide, I have a graph that shows the average temperature over the last 400,000 years and the carbon dioxide concentration of the atmosphere over the last 400,000 years. Now, correlation does not always mean causation, that is true, but we have a very large pool of data here. We have 400,000 years worth of data. And we can see that every time my carbon dioxide concentration peaks, so does the average temperature. Every time my carbon dioxide reaches a valley, my temperature decreases. So clearly these are raising and falling hand in hand. One of these clearly is causing a change in the other. So when considering your answer, remember that the colors that we see are wavelengths of light. It's a type of radiation. All colors combined, all of light, makes white light, whereas colors, or black, is an absence of all those other colors except for the one you're seeing, or black is an absence of all colors. So a light shirt isn't going to absorb nearly as much energy. It's going to take all that white light and reflect it back. So it won't absorb much, and it's going to stay rather cool. But a black shirt is going to absorb white light, like the sunlight, and it's not going to reflect much back. Black is not a color. Black is the absence of color. So a dark colored or black shirt is going to absorb most of the energy that it's hit with, and it's going to make that shirt warm up very quickly. Remember, a white shirt or a black shirt are probably both made out of cotton. Their specific heat capacities will be the same amount, but because of their color, they're going to absorb different amounts of energy. And the same thing is happening on the Earth's surface. Light is going to hit the Earth, and some places will reflect a lot, and other places on the Earth will absorb a lot of energy, which also creates an unequal amount of heating. Now, the big topic we have here is albedo. Albedo is looking at the fraction of radiation that's being reflected back to space. So looking across the globe, the Earth has more than one type of surface. We've got paved roads, grasslands, desert, ocean, snow caps. They all have their own albedos. And remember, albedo is the percentage of solar radiation that is reflected back to space. Remember, albedo looks at how much has been reflected. So land and ocean typically have some pretty low albedos. That means they absorb more energy than they reflect. So land and ocean are going to absorb a lot of energy, and they're going to heat up a lot. But snow, ice, cloud, they all have very high albedos. They're going to reflect more energy than they absorb. Objects with high albedos do not get nearly as warm. If I look at the whole planet and find about the average albedo for the whole planet is around 30%. So about 30% of the incoming solar radiation is immediately reflected back to space, and about 70% of the incoming radiation is absorbed. Some of that heat energy stays in the planet, and some of it is then re-emitted back into space. So thinking of how much energy is absorbed versus how much is reflected is a very helpful concept to figure out how much energy we're receiving from the sun and how much energy radiates back to space. Depending on the balance versus how much is being absorbed versus how much is radiating, our whole planet can be experiencing a net warming or a net cooling. Over the past 100 years or so, there's been a net warming occurring on our planet. Now, the statistic I'm giving you today is that the Earth's temperature has increased by about 0.08 degrees Celsius. Now, unfortunately, this is a number that is rising. This is not the final high temperature above average that our planet is going to reach, and you might find some slightly different statistics depending on where you look. But we have increased the temperature of our planet by about 1 degree Celsius, which doesn't sound like a lot, but it can have some pretty big effects. So let's look at a few different albedos. Down here, ice with snow has an albedo of 0.9, so that means 90% of the energy from the sun gets reflected back into space. Only about 10% of that energy gets absorbed and can be used to warm things up. If I have bare ice, its albedo is about 0.5, which means half of the energy is reflected back into space, and only half of the energy from the sun is able to be absorbed in order to raise temperatures. And then I have open ocean. My open ocean's albedo is about 0.06, which means it's going to reflect only 6% of the energy from the sun. The other 94% of that energy is going to be absorbed by the ocean to help warm it up. So the lowest albedo would be the open ocean. It reflects the least amount of sunlight and absorbs the most. My ice with snow has an albedo of 0.9, so 90%, will reflect the most sunlight. So the one that's going to warm the most easily is going to be the open ocean. It's absorbing all of that energy. 94% of that solar energy is being absorbed by the ocean, compared to only 10% when you have ice and snow. Now, this is very important for the ice albedo positive feedback loop. So a positive feedback loop is something that keeps building and building and building. It gets worse and worse and worse. If you take a microphone and stick it next to a speaker, you're going to hear a soft hum until it quickly builds into a ear-piercing, loud screech. That's a positive feedback loop. It's going to continue to build and get worse and worse until something steps in to stop it. Another example would be an avalanche. An avalanche usually starts as just a few pebbles, but before you know it, it's half a mountain is falling down a mountainside until it runs into something bigger than itself to stop it. The ice albedo positive feedback loop is a little sad. The temperature of the Earth is gradually warming, which causes more ice, mostly ocean ice, to melt. Melting that ocean ice exposes more ocean water. Ocean water has a much lower albedo than snow and ice, so that ocean water warms up more, which causes temperatures to increase, which means more snow and ice are going to melt, which means more ocean is going to be exposed, which means it's going to absorb more energy from the sun, which means it's going to increase temperatures, and it keeps going and going. So I keep having increased temperatures, which leads to more snow melt, which leads to increased temperatures, and it's a positive feedback loop. It continues to feed into itself. Now, this is the last slide we got to today in our classes, but I would like to go over the last 4 slides now in our video lesson. So human activities have affected the overall albedo of the planet, and in particular places as well. So pollution can severely affect the albedo of things like snow. If there's soot or particulates in our clouds and in our snow, that can greatly decrease the albedo of the snow and the soot, making it melt that much faster. We even see it a little bit here. We tend to see the snow get pretty dirty on the edges of parking lots and get kind of covered in the different types of salts and dirt. That ice and that snow is going to melt a little bit faster than it would if it was pure white. Another interesting thing is something called the urban heat island effect. Now, there's actually a few different reasons why cities tend to be so much warmer than their rural surroundings, but one thing is all the pavement, the paint, the construction tends to absorb a lot of energy. This is why if you've seen any recently built elementary schools here in Montgomery County, when we build schools now, we tend to give them green roofs. We tend to plant plants, grass, little gardens, not big gardens, but little gardens on the roofs of our buildings now. And part of that is to increase the albedo, so that the building isn't absorbing as much energy, but actually helping to reflect some of the energy instead, and since it's plants, reduce carbon dioxide in the area. Now, our atmosphere makes life possible on our planet, and not just because it gives us air to breathe, but because it helps keep us warm. It acts like a greenhouse. Greenhouses are used so that we can continue to grow plants in cold regions and during cold times, like during the winter. Light energy is able to get through those glass windows and the glass walls, but then it gets trapped. It heats up the air inside of the greenhouse. The greenhouse tends to be somewhat of a closed system, so that hot air can't escape. It is trapped inside the greenhouse and just gets warmer and warmer. It's not able to radiate the energy out quite as easily. So when sunlight heats the Earth's surface, some of that heat radiates back into the atmosphere. Some of it is reflected back into the atmosphere. Some is re-radiated back into the atmosphere. The atmosphere absorbs that heat energy from the sun and from the planet, and then it can send it back down to the planet. Some of the energy gets sent out into space, but some of it is re-emitted back towards the planet. Because of the greenhouse effect, we can have temperatures that are warm enough to sustain life. Without the greenhouse effect, our planet would be about 20 degrees colder, and nothing would be able to survive. Our planet would be a snowball Earth at that point. Now, when most of us hear about the greenhouse effect, we normally think of it as being a bad thing. But it's the new human-enhanced greenhouse effect that we worry about. There is a natural greenhouse effect, which is good, we depend on it, but because of our actions, because of our burning fossil fuels and our industries, we've enhanced this to a point where it's heating us too much. It's warming the whole planet beyond what we are used to, beyond what we're comfortable with, and beyond what we can predict for our climate and for our weather. So, like a blanket when you're sleeping, the greenhouse effect helps keep the planet warm, just like a blanket helps you to keep warm. But just like having a blanket while you sleep, one blanket is great. Maybe it's a really cold night, maybe you need 2 blankets, but if someone were to put 10 blankets on top of you, you'd be uncomfortably warm very quickly. I'd also wonder why they have 10 blankets just lying around to give to you. So greenhouse gases, not all of them are super bad, it's just how much of them are there. And a lot of them are natural. Carbon dioxide, water, methane, ozone, nitrous oxide. Those are all some pretty naturally occurring chemicals. But because of industry, we also have chlorofluorocarbons, which are man-made. They used to be used to help cool down things in refrigerators. Now there's too much of those gases in our atmosphere based on our activities. So now the greenhouse effect is too warm. Now carbon dioxide is the one that gets the most, let's say, press. It's the most famous of our greenhouse gases. The interesting thing though is it's not the most impactful. Water, H2O, is one of the most impactful greenhouse gases. But you don't hear about that one as often because we don't worry too much. Water has that very high specific heat capacity, so it has the potential to raise the temperature and to absorb a lot of heat. But it goes into the atmosphere and then it gets rained out again. So water, H2O, is a greenhouse gas. It's a very potent greenhouse gas. But when it goes up into the atmosphere, it comes back down pretty quickly. The carbon dioxide that we're putting into the atmosphere, that is staying in the atmosphere. That carbon dioxide isn't lowering. It's not coming back down to Earth like our water is. So, some of our major greenhouse gases include carbon dioxide, methane, nitrous oxide, ozone, and carbofluorocarbons. There are a lot of natural sources for carbon dioxide: volcanic eruptions, decomposition of remains, breathing, and the burning of fossil fuels is not really considered a natural source of carbon dioxide. That does happen a little bit naturally, but it's much more done from human activities now. Methane, it comes naturally from the decomposition of plant matter, biochemical reactions like cow burps. Nitrous oxide and NO2 are produced by bacteria. Now it is also produced by some factories. Ozone is a good greenhouse gas to have. The ozone that's in our upper atmosphere is different from the ozone that's sometimes created as a byproduct in smog. The ozone that's already there is coming from atmospheric processes, and it's fine. We want that ozone. And then chlorofluorocarbons are entirely man-made. These were discovered within the last 150 years. They are not naturally occurring, and they've done a lot of damage to the ozone layer and have greatly increased the effectiveness of the greenhouse effect. In the 1990s, there was an international agreement made between many different countries that said they would stop producing chlorofluorocarbons because they started to see the huge impact it was having on our atmosphere. Now, I mentioned before, carbon dioxide is the most famous of greenhouse gases, but it's not the most potent. One methane molecule can trap 23 times more energy than one molecule of CO2. Thankfully, there is not nearly as much methane in our atmosphere as there is carbon dioxide. And then CFCs can trap more than 10,000 times more heat energy than carbon dioxide. But carbon dioxide is the one that we focus on the most because of how abundant it is. It is the largest piece of that pie of all the different chemicals that make up our greenhouse gases. Carbon dioxide takes up most of it, and it's the one we've been focusing on. It's the one that we see those very close correlations with. And carbon dioxide is largely being increased in the atmosphere due to our actions. There's 8 billion people on this planet. There's at least 1 billion cars on this planet. That's a lot of combustion. That is a lot of carbon dioxide that we are producing every day. So remember, your homework is in the 3rd week of quarter 4 module. You need to do 2 different gizmos. Make sure you're logged into the explorelearning.com website so you're not constrained by the 5-minute trial period. There's 2 different gizmos. Make sure you follow the instructions. I noticed a lot of people in the calorimetry lab were not setting up their lab the way they were supposed to. So be careful with that. Make sure you're setting it up properly, because it's one of those types of gizmos where it tells you what to do and you need to make observations based on what you see. All right, well, we're going to have another alt task on Thursday and Friday. Until I see you guys then, make good choices and stay safe, everyone.